I wanted to go through and make a video kind of re-explaining, maybe a little bit slower, maybe a little bit more focused on how to do molecular orbitals like we talked about in class. So first thing, as we talk about molecular orbitals, we start off with atomic orbitals. So I have a nucleus, I have an atomic orbital around it, a nucleus, an atomic orbital. So as individual atoms, they are separate atomic orbitals. And we have two of them. Now, when they actually start forming a bond, we still have to have two orbitals. So as these come together, we form a bonding molecular orbital and we'll also form an anti-bonding molecular orbital. So there's still two orbitals. It's just they're not the same anymore, but just separated. They are being shared between the two nuclei. Now, as we look at the anti-bonding and the bonding molecular orbitals, I'm going to shift this down just a little bit. And if I'm looking at energies, if I'm looking at energies, let's draw a line like this. We have a certain amount of energy that the atomic orbitals have. And we can see that the anti-bonding molecular orbitals have higher energy, and the bonding molecular orbitals have lower energy. So these will fill with electrons first. So, okay, we have unbonded atoms, and we have a covalent bond over here. So this is our before, this is our after. Now, we follow this theme through when we start looking at molecular orbitals. So if I looked at something like, dilithium. For all the Star Trek fans out there, yes, I am picking dilithium because it is mentioned prominently in Star Trek. But is it an actual compound? So I start off with my 2s orbital for one lithium, and the 2s orbital for another lithium. Again, I'm just looking at the valence electrons. I don't really care so much what's buried underneath, but I'm looking at the valence electrons. And lithium brings one valence electron to the party. So there's an electron that it brings, an electron that this one brings. Okay, so we're going to have a bonding molecular orbital. And rather than writing out molecular orbital each time, we tend to abbreviate it as MO. And we're going to have an anti-bonding molecular orbital. So just like we had up here, higher energy, lower energy, we have the higher energy molecular orbital, this is the anti-bonding one, and the lower energy molecular orbital is the bonding one. Well, our electrons, and perhaps I should go through and color code these a little, just to make them pop a little more in the page. We have two electrons, two valence electrons to work with, and they are going to go in a paired fashion, because there's only one orbital, there's only one bonding orbital down here, and it makes a bond. Dilithium would be a stable molecule. It could be a real thing. I have never been around dilithium. In fact, lithium really doesn't care so much to have that extra electron, so its electronegativity is really weak. Probably falls apart pretty easy, but in theory, it should have a bonding order of 1. So if we look at our bond order, it's the number of bonding electrons minus the number of anti-bonding electrons divided by 2. So we have 2 bonding electrons, and we have 0 anti-bonding. So, in theory, it should have a bond order of 1. Okay, this one, dilithium, is convenient because, well, it only has s orbitals to deal with. Let's deal with something that has a p orbital. So, I'll switch colors here, and let's do good old-fashioned oxygen. So, each oxygen brings 6 electrons to the party, just in terms of valence electrons. So, okay, how does this get put together? Well, if we look through and look at oxygen, we should have some s orbitals. We should have some p orbitals. I want to do these bigger. Okay, so 1, 2, 3. There we go. I like that better. Okay, so the s orbitals are easy. There's an anti-bonding. There's a bonding. When we look at the p orbitals, well, we have some sigmas, some sigma bonds and some pi bonds. So we're going to have one sigma. Yeah, I don't like the way that looks. And we're going to have a couple of pi's. And we have the same thing kind of on our anti-bonding side. So 3p orbitals. 1, 2, 3 bonding. 1, 2, 3 anti-bonding. Okay, so 12 electrons. Let's go for it. We have 1, 2, 3, 4. Again, as we look at just the oxygen, those 6 valence electrons that it brings to the party, it would have a pair in the s orbital, and it would have, so that's 2, 3, 4, 5, 6 in the p orbitals. So we have that is what we're seeing down there. We need to replicate the p's the same way. And the other oxygen is doing the exact same thing. Now, I'll also point out, I was taught where the arrows cross the lines. I think some books are where the arrows sit on top of the lines. It does not matter. It does not matter at all. Okay, so I have 6 bonding orbitals. I have 8 electrons altogether. So I have, and I have my 4 electrons here. So 1, 2, 3, 4. I have 8 electrons here. 1, 2, 3, 4. Now, again, Hund's rule. Those electrons are going to go in unpaired if they can. You're going to get a room to yourself if you have the opportunity. You're not going to leave an empty room just so you can have a roommate. You're going to have your own room if you can. People like privacy. Electrons like privacy. So, 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. So those 2 electrons go into orbitals individually. So, okay, if I'd had more electrons, I would keep filling up here, but I don't. I have 8 in the p's. That's all I have to work with. So our bond order, again, is the number of bonding electrons minus the number of anti-bonding electrons divided by 2. So our bonding electrons, those would be bonding electrons. Those would be bonding electrons. Trying to grab just that one. That would be a bonding electron. Trying to take those lines back to their original color. So we have 1, 2, 3, 4, 5, 6, 7, 8 8 bonding electrons. And we have 1, 2, 3, 4 anti-bonding electrons. Divide all that by 2. We would have 8 minus 4 would be 4 divided by 2. We would have a bond order of 2. And generally, as we would draw the Lewis dot structure for oxygen, we would probably draw it with a double bond to make sure that everything had a nice octet. So it corresponds, it agrees with what we've done with the Lewis dot and valence bond theories. Valence bond theory says that each oxygen can form 2 bonds because it has 2 unpaired electrons. So everything is agreeing nicely. And that's a good thing. So last little bit, I want to talk about those electrons up above. Actually, let me do a different color. I'll do green. These unpaired electrons make O2, oxygen, a paramagnetic substance. It's attracted by magnetic fields. If we'd only had something like this, so like our dilithium has only paired electrons, it would be diamagnetic, and it would not be attracted to magnetic fields. But these unpaired electrons up here make oxygen a little bit special. It will be attracted to a good, strong magnetic field. Okay, this video's probably gotten long enough as it is, but I thought it might be nice just to kind of go through it maybe a little bit slower, a little bit more methodically. Hopefully, you'll find this helpful.